Picking up where we left off with the last video, we were talking about how we know whether a function is increasing or decreasing based on what the y values are doing. Remember, when we answer the question on what interval is the function increasing, the answer to that is always a set of x values. Okay, the y values are what you are comparing, okay, to make the conclusion about increasing or decreasing, but the conclusion is an interval on the x-axis. Says finding the largest or smallest values of a function is important in many applications. A lot of times you guys have done these where we want to maximize a profit, maybe minimize a cost. You've done questions where, like, if a farmer has like 200 meters of fencing and wants to maximize the amount of area that they are going to enclose, but they're going to use one side of a river as one boundary. What would be the maximum area that they could enclose with this 200 feet? So tell me what the dimensions of this field would be. You've done questions like that in Algebra 2. They're called optimization problems. We might investigate a couple of those in this class. We might be able to optimize, like I said, profits. Okay, so if I have, let's say I'm a farmer, and I know that if I take, based on supply and demand, if I go to the market today with all of my oranges that I've grown, I might get $2 per bushel. Okay, but if I wait until next week, some of my oranges are going to rot, so I'm going to have less bushels, but the demand is going to go up, so I might get $2.25 per bushel. So then I got to decide, okay, well, is it more lucrative for me to go now when I have all of my produce fresh and get a less price for more bushels, or should I wait a week and get a higher price per bushel, but for a less total number of bushels? How do I maximize that profit? These points allow us to do this, okay? And the algebra and ultimately the calculus will allow us to find these maximums and minimums, okay? But it's all predicated off of knowing that maximum is the transition from increasing to decreasing, and a minimum is the transition from decreasing to increasing. So we can easily find these values from a graph of a function. We first must define what we mean by a local maximum or minimum. Okay, so local means in a vicinity, a neighborhood, if you will. It says local maximum and minimum of a function. It says the function value f of a is a local maximum of f if f of a is greater than or equal to f of x, where x is near a. Okay, so when we get to calculus, we'll be a little bit more specific with what this near means, because it's kind of vague. It's a little bit ambiguous. But let's look at our picture over here. Okay, I'm going to call this point right here A. Okay, and I'm going to refer to these values here. I think you guys can all argue that near A would be values like these here. So I'm going to call this x1, x2. We can have all kinds of x3, 4, 5, whatever we want through there. Okay? But my argument is, if I look at that point right there, f of a, would you agree that that f of a is greater than or equal to the f of x sub 1? Because that's an x value that is near or close to the x value of a. Would you also agree that f of a is greater than f of x sub 2? And if this was like f of x sub 3, maybe that one there is f of x sub 4. This f of a is greater than all of these f of x's that are in that little neighborhood. Okay, so basically what this is saying is if I look at this function, and when it says when x is near a, basically what they're telling you to do is narrow your purview, your scope, and just look at maybe, that's a terrible, all right. So what it's asking you to do is narrow your view on just that box. Because you know there is a maximum in there. Okay. How do I decide what point is the maximum? How is it defined? It is the largest y value in that box. Okay. And this here, those are the x values that are near the x value of a. Okay. So that's what that argument is saying. So that would be called what we call a local maximum. We do the same thing over here. There's another local maximum. And then the logic is consistent for minimums, but now this point here just has to be that's f of a again. That just has to be less than all of these other f of x's that are in its neighborhood. Okay, so that is what we refer to by definition what a local maximum and local minimum are. Okay, now let's say that this graph, let's see if I can wipe all this stuff off. Okay. So let's say that this graph were to have, let's say it stopped right there and it stopped right there. Okay. If it doesn't do that, we're going to anticipate that it extends forever, even if it doesn't have arrows on it. If I did this, now it does not extend forever anymore. Okay. So not only do we have, this would be a local maximum, local minimum, local maximum, local minimum. But this point here, that f of a is greater than all f of x's. Okay? And if that's the case, it's still considered a local maximum, but it actually takes, it's like the idea that an isosceles triangle is equilateral. Let's rephrase that. An equilateral triangle is isosceles, but a lot of times I don't refer to the equilateral as being isosceles. It has a better classification. So this is still a local maximum, but because of this, because of being the largest y value on the entire graph, has a better classification, and we call it a global maximum. Maximum. Okay, a global maximum. Let's see here. We can have global minimums as well. Okay. Now there would be a debate here. What is that y value there the same as that one? This one looks kind of lower, so that would be maybe the global minimum. This here is a minimum, but it's not a global minimum. It's not the smallest y value. So those are little things to think about as we progress through here. You're going to see the word extremum, extreme, and I believe that is the plural version of local and local maximums and minimums. Okay, so I'd be saying all of them. Okay, and extreme is the singular version of. So this would be an extrema. This is an extrema all by itself. And you can see that in GeoGebra. If I were to take a function, let's say I have these points, and I'm just going to go fit poly between A, B, C, D, and E, E. So let's say I have that, and I ask it to find, I come over here to the point, see where it says extremum. If I click the function, it's going to give me those extreme values and give me all three of them. Okay, F is an extrema. If I look at F here, I think you guys can argue that Y value of 10.15 on this entire function, no matter where I put a point. Okay, so let's look at I. Let's make it red. Okay, so if I look at I here and I start moving it, and I compare I to this point F here of 10.15, let's make that point. I'll make that purple, maybe. Just kind of want to give you a way to see over here, distinguish it over here. Can I move it? I can't. I think I can do this though. Yeah. Alright, so if I compare that number right there, that Y value, and that Y value, the Y value of I is never going to be greater than the Y value of F. Okay, now they could be the same, okay, but the Y value of I will never be greater than the Y value of F. So, and that's everywhere on this graph. So that tells me that F is a global maximum, okay, an overall maximum, okay. Now, if I come over here and I look at this, okay, will I ever, so I look at this value of G, so let's put G down here. So looking at this Y value of G and this Y value of I, okay, in this vicinity, in this neighborhood, I will never have a Y value that is less than G. So G must be a local minimum. Now the question is G a global minimum? Well, if I move I all the way over here, is that I value's Y coordinate smaller than that Y coordinate? Okay, so I is more minimum now than what G's Y value was, so G is not a global minimum, okay? And in this particular problem, it doesn't have a global minimum. There is not a global minimum here, because this is going to go down to infinity, and if I could identify what infinity was and actually indicate it, then the idea would be that infinity is a number, and I don't know what that is. So when it continues on forever in either this direction or in the positive direction on the y-axis, you do not have a global minimum, or if it was maybe reflected. So if, let's see if I have what opposite of f. So if I have this red function, okay, now I'll have a global minimum down here, but I will not have a global maximum anymore because it's going to infinity, and I don't know what infinity is. I can't define it. The one thing to think about is when it asks you what is the maximum, okay, when it asks the question what is the maximum, that is asking what is the y value, what is the largest y value. So the answer to the question what is the maximum, it is the y value, okay. Here it says find the local maximum and minimum values of the function x cubed minus 8x plus 1 rounded to 3 decimal places. What I want to do here is I want to kind of investigate this the way that we know how with our skill right now, with our level of knowledge, our depth of knowledge, but then maybe give you a little bit of an insight in where this is going to be taken in calculus. So right now, the really only thing we can do is we can look at a function we can say f of x equals x cubed minus 8x plus 1. We can look at this and we can ask ourselves, okay, where is the maximum and minimums here? Okay, so I can click on that extremum, and I can click the function, and now it tells me that the maximum is here at point A, which is a y value of 9.71. So that's the maximum, and it's a local maximum. And then negative 7.71 is going to be a local minimum. Okay, and you can see what happens here is a maximum is the transition from, if I said if, let's see here, if x is less than the x value of a, then graph this. If x is greater than the x value, don't worry about what I'm typing in, I'm just trying to get this thing to have some conditional formatting. Different colors for me. Okay, I shouldn't have done it that way. Okay, so that's good enough. You see that in the red or maroon that we are increasing, and when we get to the blue, we start to decreasing. So that transition, that change from increasing to decreasing is at point A. That means increasing, now decreasing. That means that must be a maximum. Okay, and right now the only thing that we can do is use our graphical approaches here. Okay, now I'll show you on your TIA 384 is how you can do this if that's what you prefer. I hate TIA 384 because it's cumbersome. I think the best thing, to be honest with you, even though I think Desmos is problematic. It's nice for like Algebra 1, Algebra 2, but there's a lot of hidden stuff that just kind of hard to get to function the way we want it to. Maybe I don't know if that's the best way of phrasing it. I prefer GeoGebra over Desmos. But one thing about Desmos that is nice, 8x minus 8x, is like there's no extra tools that I have to go find. I actually just click on this. It'll put these gray dots and it'll tell me what those coordinates are of the maximums and minimums. Okay, so that's nice, but there's a lot of things that Desmos doesn't allow me to do, and one of those things I'll show you here in a moment. If I'm going to do this with my TIA 384, so I'm just going to show this one time, and then however many times you need to kind of pause and review this, I'll let you do that. So you're going to go to Y1, and you're going to type in x cubed minus 8x plus 1. I'm going to graph it. The one thing I don't like about this is, if I'm graphed here, sometimes my window might be zoomed in like this from maybe the last question that I did, and it's not as easy as if I'm in Desmos. All I'm doing right now in Desmos to zoom in and out and to pan around here is using the wheel on my mouse and clicking and dragging. On this, obviously we don't have that functionality. I have to go to zoom, and I have to be able to navigate and understand what these zoom options provide me. If I'm not certain, I want to go back to kind of the default zoom of the entire calculator. Like when I bought it at the store, it was under option 6 here, zoom standard, and it just goes 10 by 10. That's actually 20 by 20 view screen. Right now it gives me a good view, so I'm not going to mess around anymore with it, but I'm going to try to find what that ordered pair right there is. So you can trace over here, okay, but that's just an estimate. That's due to the pixels and all that kind of stuff. These are just estimates, okay? They're not really good solutions. What I need to do is I need to go second, hit the trace button, which is actually going to take me to the calc tools. And what am I looking for here? I'm looking for a minimum. So I'm going to hit option 3. And now all it does is says, okay, well, what's your left bound? So I'm going to go close to my minimum, just because if I'm far away from it, it's just going to create more computing needs. It's going to require more RAM. It's going to slow my calculator down. And sometimes, depending on how intricate my function is, it might actually shut my calculator down. So I don't want to go real far away from this. It's also going to confuse things if I'm to the left of another extreme. So I'm going to get close to where I think my minimum is, and we'll hit enter. Okay, and I'm on the left-hand side of where I think that point is. Now it says, what's your right bound? So here's my right bound over here somewhere. Okay, and what we just did was this idea right here, where we took this box and we put a box around there and basically applied the definition here of X being near A. We now narrowed our view between, you see these two little arrows that showed up. We've basically now narrowed our view in here. And what our calculator is going to do when I hit enter again is it's going to analyze all of the Y values in that box. And it's going to find the smallest Y value. So hit enter a third time when it says guess. And now you see it puts my cursor down here. And the Y value then right there is the minimum of that particular function. Okay. Now, that's the only thing that we have the ability to do right now in this class. Okay. But let me show you something that might be of benefit to see where this is being taken in calculus. So let's see here. All right, so what happens in calculus is that we want to talk about the slope of this curve at any particular point on the curve. Okay, so if I want to know, what is the slope of this curve if I am standing at point C? Okay, my hope is that you would argue that the slope there is maybe more steep than if you were standing right there. Okay, which both of those might be less steep than standing maybe right there. Okay, so the idea about slope on curves is that they are ever changing. They're always different depending on where you are located. And part of calculus is kind of understanding that and analyzing that. But what we learn is that, and I'm just going to give you this visual real quick, if I just zoom in on one little section of this, okay, it looked like a curve to begin with, but now that little section of the curve looks like a line. And if I can determine what the slope of that line right there is, or what looks to be a line, I should then have an idea of knowing what the slope of that curve is at point C. And the idea of that is this. So let's say I'm going to put another point on here. And we'll connect these with a line. Okay. Now, if you remember in geometry, when I had a circle and I had a line that passed through a circle 2 times, that was called a secant line. This black line is referred to as a secant because it intersects my curve 2 times. I'm just going to make it dotted right now. Okay. Now here's what we do with calculus. In calculus, if I look at that line right there, the slope of that line right now is this right here, 7.96. Okay. So the argument in calculus is, well, because that line right there, that black or that dotted line is a approximation, it's a close representation of the slope at D. Okay, they're an estimate one another. But right now, because there's such a distance between C and D, it's kind of a cruddy approximation. So what we do is we move this point C, which I've got stuck right now. Oh, I think it's because, let me do this. The way I created C, it was static, but now same thing's happening there. All right, it froze on me, so I had to restart. So put this secant line in here again. And the idea then is if I want to know what the slope is at, let's say, point D, is what we try to do is we try to make this secant line be created so that this distance between C and D is as small as possible. And we say that we need it to be infinitesimally small. Okay? Because the idea is as long as I've got 2 points, I can always do the slope formula or the average rate of change formula between those 2 points. Okay? But what we do is we say we want that to be infinitesimally small, and when it's infinitesimally small, I'm going to zoom back out, we make the estimation, approximation, that those 2 points are actually the same point. And that secant line now turns into what we call a tangent line. Okay? So right now, the slope of this line right here, so the slope of this line would be 7.51. So basically what I'm telling you is that if I ask you what is the slope of this curve at the point x being negative 2.27, what is, if you're standing at negative 2.27, what's the slope of the curve? You would say it's 7.51. Okay? Well, when we're working with extremums, okay, those points are very interesting. Those slopes are very interesting. Look at this slope here. If we did that of this tangent line, that slope is becoming what number? Or what kind of line is our tangent line becoming? It's becoming a horizontal line. And the slope ends up being 0. Okay? So the slope of tangent line is 0. If we can determine that, that's going to help us determine algebraically where that point happens. And so in calculus, we're going to be able to find out a function g of x, which is going to be, in this case, going to be 3x squared minus 8. Okay, which I developed that solely from this function here. Okay, I won't explain how I get that, but it's very easy. And now what I'm going to be asked to do is where does that equal 0? Because what's really happening there, because this is ultimately the equation. It shows me what the slope is at all of these points. Okay, so remember, right here the slope was 0. Okay, of that tangent line. So if I said when does 3x squared minus 8 equal 0, so I want to say solve 3x squared minus 8 equals 0. I think I have to tell it for x. Nope. It gives me these two values right there. Okay. Which if I type one of those in, let's go negative 2 square root of, so I'm multiply negative 2 times the square root of 6. and then we'll divide that by 3. You see you get negative 1.63, which is the exact location of that maximum on our curve. Okay, so the whole grand scheme of things, what I'm trying to explain to you here or show you is that right now we are limited in how we can find maximum minimums. Okay, and we are limited because of our algebra skills to just being able to, at the moment, using technology. But that's going to quickly change, and we'll soon be able to find those maximum minimums algebraically or analytically. Okay. Here are some questions that are going to kind of encapsulate all the concepts we've been talking about in the last couple of days. The first one says find the following. So find g of negative 4. Okay, so this function here is g. Okay, it's a piecewise function. Pass the vertical line test. The only question would be, does it pass the vertical line test right there? And it's an open dot and a closed dot, so it does pass. So if it asks me what's g of negative 4, okay, so I'm going to go find negative 4 on my x-axis, because remember that's my independent value, so that's my x value. I'm going to say, okay, what is the y value on my graph that is attached to x being negative 4, and that y value would be 5. So g of negative 4 is equal to 5. That yields the ordered pair negative 4, comma 5. Okay. All of these ordered pairs are going to be of the format x, comma g of x. An independent value, comma, the function evaluated then at that independent value. G of negative 2. So we'll find negative 2 on my x-axis. And we'll go up then 1, 2, 3, 4. So g of negative 2. G of negative 2 is 4. G of 0. X value is 0. Well, it turns out the y value is 0. So g of 0 is 0. Okay, so again, I'd have the ordered pair from this one, negative 2, 4. Here's going to give me the ordered pair 0, 0. G of 2, 1, 2. So now, there's a debate. Which one of those do I choose? Well, remember what this symbol here means. It means you're getting up to just the side of 2. You're getting to 2.01, 2.001, 2.0001. But right there, you never get to 2 right there. But down here, it's saying you can get up to 1.9, 1.99, 1.9999, and you can make the leap and get to 2. So when x is 2, in this case, the y value is 3. So g of 2 is 3. Question was g of 4. G of 4 would be a height of 2. So again, I'd have the order pair 2, 3 from this. And from this, I'd have 4, 2. If I ask you what's g of 5? G of 5. Well, 4 would be here, 5 would be there. What's the y value that's graphed there? Undefined. Okay, it's not graphed. All right, so that's finding those individual values. I'm really having troubles with my scrolling here. All right, so those are my individual evaluations. Now ask me for my domain. So remember, when we do the domain, we're asking if I were to take that bar and drag it left to right through my graph, what's the first x value I come in contact with? It'd be negative 4. And I just keep track of x values that are going to maybe potentially get kicked out or be a problem. And there could be a problem here, but it's included, so I will have an x value of 2. So there's no problem there. And the last x value I come across would be 4. So my domain would be -4 up to, in this case, +4. Now if it asks me for my range, very similar procedure, but now we are going to use that line right there, and we're going to move it from bottom up. So the first y value you come in contact with would be 0. So 0's going to be my starting point for my range. And then I keep going through, and people get to here and say, well, there's an issue because now I got 3 things. That's fine. There's still going to be a y value that's going to be attached to 2. Okay, so you're good. You're good here. Still intersecting the red, still intersecting the red, still intersecting the red somewhere. Still intersecting the red somewhere, and I get to here. And the question is, well, does that value of 5, is it included? Because it's an open dot there, but it's closed up there. So it is included. So what we see here is that our range started at 0, and it goes up to 5 and includes 5 because it's closed there. If they were both open, there would be a parenthesis around 5. All right, so then we got to determine where are we increasing or decreasing. Well, if I start here at -5, and this is what we talked about, I guess it's -4, you're never going to increase or decrease with brackets. They're going to be parentheses because I'm right here. I'm going to be not doing either, okay? So I'll say -4, and I'm going to move to the right. So starting on an x value of -4, as I move to the right, I want to get to right here. And at that point, beyond that point, I'm going to be moving upward. I'm going to be increasing my y's. So that set of x values from -4 to 0 is a set in which I am decreasing. Put it on the wrong block there. Okay. Then what's going to happen is you go from 0 and you're going to walk to here, and now we are increasing. Okay, so we're increasing from 0, and that was on the interval from 0 to 2. So remember, we're always answering increasing or decreasing using the x values. Okay, then from there, from an x value of 2 to an x value of 4, you'd be walking down. So you're back to decreasing from 2 to 4. We'll union anything, and whenever we have multiple intervals of these two behaviors, we will be unioning it. Now it asks me for a maximum min. Well, right now I know I have a minimum right there. Okay, so my minimum would be 0. Okay. Now the question is that local? It is local. Any minimum is local. Okay. But is it the smallest y value of the entire function? And it is. So 0 would actually be called a global minimum. Okay. Now, when I look at these other points here, okay, we can argue that in that area right there, that point right there, it's a y value. It's not a peak, okay, and it's not a valley, okay, but it is the last value of my function on this interval, and it's bigger than all these other values that are in the neighborhood. So that point right there, when x is -4, and y would be, what, 5 there, so a y value of 5, that would be a max. Okay, and it turns out that it's actually the largest y value on the entire function, so that would be a global maximum as well. This point here, would you agree at that point is kind of the largest in its neighborhood? Okay, so we would consider that a local maximum. Here's a local minimum. Now here it's going to be hard to determine because I'm not going to necessarily be able to tell what that maximum is because it's open. So it's like 2.000000000001. So there's kind of discrepancy on how we're going to write that. But this is the idea of being able to look at a function, determine the domain, the range, where it's increasing, where it's decreasing, maximum, minimums, and that sort of thing. A lot of times the questions aren't necessarily going to be piecewise functions when you're asked about max and mins. They're going to be more like this, okay? So they're going to ask, where is this thing increasing and decreasing? So what I like to do is, like I said, put myself on the graph and say, okay, right now I am moving left to right. We always read graphs left to right. So right now I'd be decreasing. And at that juncture, at that point right there, that behavior starts to change because now my y values, as I move to the right here, my y values are going up. When I get to that point, now I see that my y values are going to be moving down again. And I get to that point, as I continue to move to the right, my y value is going to go back up. All right, so that shaded colored region is showing me what my y values are doing. But remember, I always write my answer about decreasing or increasing as an interval of x values. So this blue is my y values. What interval of x is that set of y values being established for? And it's these x values to the left of 1. So we are decreasing, going left to right, we are decreasing on the interval from negative infinity up to 1. All of these values over here are y values, or producing y values, that as I move to the right, as I move x's to the right, my y values are getting smaller and smaller successively. I get to 1, okay, and now I've got this interval between 1 and 3 where my y values from left to right are going up. So 1 to 3, I'm increasing. Then from 3 to 4, you see your y values are now decreasing. So I'm going back up here. 3 to 4 is another interval for decreasing. And then 4 this way, 4 that way, you are continually increasing. And I know it's always because we've got arrows here. So I'm going to infinity with these arrows. So increasing from 4 to infinity, then we'll union these. And what we recognize is that we went from decreasing to increasing, so there is a minimum. Okay? And the minimum value is -1. It's the y value. We go from increasing to decreasing here, so that is a maximum there. And then from decreasing to increasing, that point right there is a minimum. Now, we'd like to talk about, is this the lowest y value of the entire function? And I think you can argue that there is no y values that are on this graph that are below that. So this is a global minimum. Okay. Sometimes a synonym from global might be absolute. Okay, they mean the same thing. Global minimum or absolute minimum. This here is a maximum, but it's not an absolute maximum because there's y values that are bigger than it. Okay, and because this thing goes off into positive infinity, there is no global maximum. Okay, because I don't know what infinity is. That point's a minimum, but it's not a global minimum. Just because of time running out here, I'll let you kind of attack these other examples on your own. Graph these, determine what you think to be the maximums, minimums, this is just an example where if I've got this function here that is it's on a closed interval, this is an absolute maximum. Okay, even though it's not a peak, we're not at a transition from increasing to decreasing, but we do chop the graph off here. It's finite now. That would be the largest y value on the graph, so that is a maximum, and it would be the absolute maximum or global maximum. Here would be an absolute minimum or global minimum. This would still be, if I look at this, that is still going to be a maximum. That's the largest y value in that neighborhood, so that'd be a local maximum. So those are things to consider as we start to analyze these points. But this main vocabulary here, the purpose of it is so we can have dialogue about maximums and minimums in those relationships for other types of functions. Maximums and minimums for the various polynomial functions that we're going to come across. Maximum, minimums for trigonometric functions and so forth.